Hello dear students, hope you're all doing well. In this video I'm going to talk about chapter 6 section 5 molecular geometry. Let's begin. The properties of molecules depend not only on the bonding of atoms but also on molecular geometry. Guys, properties of molecules, we all know a molecule is made of covalently bonded atoms. When we say covalently bonded atoms, means there is a covalent bond between atoms. When two, like H2O is a molecule, 3 atoms, 2 hydrogen and 1 oxygen, they are covalently bonded to each other. So there is a covalent bond between them. Basha. So properties of molecules. We learned about properties of molecular compounds because molecules, they make molecular compounds. We learned about their properties that we said some of they have high boiling point, low boiling point molecular compounds compared to ionic compounds, right? So these are properties. So the properties of molecules do not only depend on the atoms, bonding atoms, single, double bond, okay? So we have something else that affects the properties of molecules, which is molecular geometry. So molecular geometry is important because it affects the properties of molecules, means it affects the properties of molecular compounds. Okay, what's molecular geometry? Molecular geometry is three-dimensional arrangement of atoms of a molecule in space. We want to know how the atoms are arranged in space. Look at here, guys. These are some shapes of molecules. This is so in 3D, a molecule, how it's arranged, how the atoms are arranged in 3D. So affects the property, means shapes of molecules. Okay, molecular geometry, we can say it's shape of molecules. Basha? So to know the molecular geometry, to study molecular geometry, what do we use? Whisper theory. Okay, this is a theory we use to predict the molecular geometry. So what is whisper theory? Valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. So what does it mean? This theory states that repulsion between the pair of valence shell electrons, bonding or non-bonding, surrounding an atom, causes these pairs to be oriented as far apart as possible. Guys, this theory says between the shared electrons, between the lone pairs and shared pairs, there's repulsion. Guys, this is a molecule of water. They have valence electrons. For example, oxygen here, it has how many? It has 8 valence electrons. 4 of them, they are unshared, and these lines, we know they represent shared pairs. Each line here means represent a bond, 2 electrons. So this is 2 electrons, and this is 2 electrons too. Here we have 4 or 2 pairs or 2 lone pairs, isn't it, Basha? This theory says between these electrons, these valence electrons, paired or and shared pair or unshared pair, there's repulsion, guys. These electrons, they do not have negative charge. So these electrons, this is an electron, this is an electron. Basha? Here we have These are electrons. Dots, they represent what? Electrons. Here also we have two electrons. Basha, these are electrons, electrons, electrons. Basha. Between these electrons, there's repulsion. Okay, there's repulsion between them because they are what? They are negatives. So let me, now we all know how many valence electrons oxygen has. So it has eight valence electrons. Between these, there's repulsion. This pair, this lone pair, pushes these electrons, right? The shared pair. The shared pair also like repels the lone pairs here. Between these two lone pairs, we have repulsion too. Basha? Also between the shared pairs, also there is repulsion. They repel each other. Okay? Between here also we have Basha. So this repulsion, it happens between all paired, shared pair, and these two, they are shared pair, they are shared valence electrons. These four, they are unshared, we call them lone pairs. So there's repulsion, Basha. This repulsion causes the pairs, bonding and non-bonding, to what? To be oriented, to be organized, to be arranged as far apart as possible. That like it makes them that how is it possible to like the lone pairs and shared pairs, they're going to get far from each other. So here, that's why, guys, here in oxygen, here, why it's not like that? You might ask why. Let me make it clear. Why water is not like that? Hydrogen and is not like that. Two lone pairs here, isn't it? So because there's repulsion, these lone pairs pushes these downward because there's repulsion. Between these also we have repulsion. So at the end, the shape of water molecule is going to be like that. Okay? This is the shape. Why it happens like that? Because there's repulsion between the pairs valence electrons. That's why the whispered theory says valence shell electron pair repulsion. It says there's repulsion. This repulsion causes the shared pair and lone pairs to stay or to be oriented as far as possible from each other. So here, why they're not going to be like that? Hydrogen. Because here there is repulsion. So this repulsion makes that hydrogens to be get far from each other. But here also there's another repulsion makes them downward. Basha? Also here, that's why boron, tetrachloride, the atoms, the chlorine atoms, they are oriented like that because there is repulsion between these. Basha? This repulsion that push each other and to be, they're going to stay far from each other, not get close to each other. That's why the bonding is like that. This is 3D shape, so there is a reason. So lone pairs, repulsion between lone pairs causes that having electrons, the shape of the molecules be different. Okay? Molecular shape or molecular geometry, we can predict the shape of molecule. We can determine by two factors. Number of atoms bonded to central atom. For example, here two atoms bonded to central atom. This is central atom. Others, they are bonded to central atom. Okay? beryllium fluoride here. So this is will be linear. We're going to talk about this shape is linear. But what happens is three atoms bond to central atom. This is beryllium. Okay, two atoms bonded to central atoms, this shape. What happens if three atoms bond to central atom? Look at here, its shape will be like that. So atoms bonded to central atom change the shape. What else? And here guys, double and triple bond do not change the general shape. So here, for example, CO2. If in CO2, this is a Lewis structure. Okay, Lewis structure, 1, 2, oxygen has 2 lone pairs, but carbon. So here, there's double bond, isn't it? Two atoms bonded to central atom, to carbon, two oxygens. But there is double bond, but double bond doesn't affect the shape. Okay, note this. And number of unshared pairs of electrons on the central atom. So if there is lone pair on the central atom, it affects the shape. Guys, here, two atoms, two fluorine, they have not bonded to central atom? Yes. Here, how many? Two hydrogens are bonded to central atom, means two atoms bond to central atom. But why its shape is bent, is not linear? So the reason, these lone pairs. Because these lone pairs, they push the shared electrons, shared pair, these two shared pair downward. There's repulsion. That's why the shape will be bent. Means lone pairs on central atom affect the shape. And number of atoms bond to central atom. And the double and triple bond do not change the general shape. Basha. Unshared pair of electrons on other atoms in the compound do not affect the shape. Guys, here, do you see there are lone pairs? Each fluorine has how many lone pairs? 3 lone pairs. They are unshared electrons. They have not bonded. Here also there are 3, but they do not affect the shape. What lone pairs on central atom affect the shape? Basha? Guys, there are 7 shapes. Generally, there are 7 shapes. Types of molecular geometry. Does the central atom have lone pair? Guys, there are 5 shapes that central atom doesn't have lone pairs. Basha, linear, how many atoms they're bonded to central atom? 2. This is central atom. Trigonal planar, how many? 3 atoms bond to central atom. Tetrahedral, we have 4 atoms bonded to central atom, but there is no lone pairs because here it says no, that's the central atom. But here there are 4 atoms. When 4 atoms bond to central atom, shape will be different, will be tetrahedral. Trigonal bipyramidal, 5 atoms are bonded to central atom. Octahedral, how many? 6 atoms are bonded to central atom. But does this central atom has lone pair? Yes. Guys, there are only 2 types that central atom has a lone pair. When 2 atoms bond to central atom, it might have 1 lone pair or 2 lone pairs. Like H2O we said here. 2 atoms are bonded to central atom, the shape will be bent. If there is 1 lone pair, it's still lone pair, it's still bent. And trigonal pyramidal, 3 atoms are bonded to central atom, like here, trigonal planar. What's the difference between these two? 3 atoms are bonded to central atom. But the central atom has lone pair, a lone pair only. Pasha? Look at this table. This table tells you everything about the shapes. Amana, these are the name of these shapes. There are 7, okay? So these bands, they are same, okay? Bands having 1 lone pair or 2 lone pairs. This is molecular shape of molecules in space. It's like that, okay? This one is not, just note how is it in space. It's not very important here to know. What's important, guys? This side, this column. Atoms bonded to central atom. How many atoms they bonded to central atom? 2. Trigonal planar 3, band 2, 4, 3, 2, 5, 6. You must know this. Lone pairs, this is also important because what affects the shape? Atoms bond to central atom and lone pairs. So when it's linear, when two atoms they bond to central atom, zero lone pairs. And type of molecule, guys, type, this is like a formula, you must memorize it. What does mean AB2? A, guys, A is central atom, B is the atom that has bonded to central atom. Means here B2 means two atoms are bonded to central atom. So now it's going to be linear. Pasha? For example, beryllium difluoride. I ask in the exam, what's the molecular geometry of beryllium difluoride? So you might say beryllium is going to be central and fluorines, they bond with the central. How we know it? We must know Lewis structure. Guys, here, Lewis structures are like drawn geometrically. So, but Lewis structure, when I ask in the exam, you don't need to draw it geometrically. If I ask draw geometrically, yes, here they are drawn geometrically. So here how we know? We must know Lewis structure. But sometimes it's clear, this is going to be the one that's from left, mostly is A, is the least electron negative. This is going to be A, and this is going to be B, B2, okay? Like that. So we know that beryllium in the exam, I give you beryllium, it's in group 2, it has 2 valence electrons. And there are 2 fluorines. Fluorines, they surround the least electron negative, which is central atom, and they have how many lone pairs? They have 3 lone pairs, but they have 7 valence electrons. When an atom has 7 valence electrons, only needs 1 electron, and they're going to share their valence electrons. It needs 1 electron to be 8. So it's going to be linear. It's going to bond with this beryllium. Beryllium can make only 2 bonds, exception. And here also it makes a bond with fluorine. Fluorine also needs 1 bond, needs to share only 1 electron. When an atom shares 1 electrons, an ampere, it's a single bond. We talked about Lewis structure, but how many atoms are bound to central atom? 2. Now this is when 2 atoms bond to central atom does it have any unshared electrons? No, it has shared all. It has only 2. It has shared them. So this is going to be linear. You must memorize them like that, guys. Trigonal planar. 3 atoms are bonded to central atom. Lone pairs, 0 lone pairs. And AB3, this is the type, you must know it. Guys, from the type you understand 3 atoms are bonded to central atom. A is central atom. So when you know trigonal planar, you must memorize like that. Trigonal planar means AB3. 3 atoms bond to central atom. And central atom doesn't have any lone pairs. So example, boron trifluoride. Here, look, if we draw the Lewis structure, boron is going to share 3 electrons, isn't it? It's in group 13, so it makes 3 bonds with 3 fluorine. So when 3 atoms bond to central atom, and central atom doesn't have any lone pair, it's trigonal planar. Bend, guys, bend or angular, mostly we use that word, bend. So 2 atoms bonded to central atom, but there is a lone pair on central atom. Okay, ONF here. So AB2E, guys. Here E means what? 1 lone pair. When it's E2, 2 lone pairs. So this number, E represents a lone pair. So when you memorize band means 2 atoms bonded to central atom means AB2. It has a lone pair E. Know this. So then I give an example. When you give an example, you must know how to draw Lewis structure. Oxygen ONF, guys, here, this molecule. Nitrogen is the least electronegative. Here is going to be central. Nitrogen, it makes 3 bonds. It has 3 ampere. So one is because it makes a single bond with fluorine, because fluorine makes only 1 bond, but oxygen, it has 2 amperes, makes 2 bonds. So the other 2 will bond with oxygen. Now, guys, there is double bond, but doesn't affect the shape. What's important? How many atoms are bonded to central atom? 2. And central atom has a lone pair. Here, this is a lone pair. 2 dots, 2 electrons. So this is going to be bent. Tetrahedral, 4 atoms are bonded to central atom. 0 lone pairs. The type of molecule, AB4. Example, CH4. Look, how many atoms? 1, 2, 3, 4. Carbon is central, doesn't have any lone pair. Trigonal, pyramidal, 3 atoms are bonded to central atom. Central atom has a lone pair, means AB3E. We have AB3, guys. Look. But here there is a lone pair. This is how we make the difference. NH3, when I draw Lewis structure, nitrogen is going to have a lone pair, an unshared pair. Okay? Band, guys. Another band. Actually, you can memorize like that. Band means A, okay, B, E1 having 1 lone pair, or E2. Rasha? Because it has 1 lone pair or 2 lone pairs, look, both are bent, angular. So, but here there's 2 lone pairs like H2O. There are how many dots? 4 dots mean 2 lone pairs. Basha, trigonal bipyramidal, 5 atoms are bonded to central atom. And this is AB5. The type, phosphorus pentachloride. Here, do you see? This is what? The Lewis structure of it. If I ask for Lewis structure, you're need to draw it. But in 3D, this is 2D. It's not clear how is it in 3D. Octahedral, atoms bond to central atom, 6, 0 lone pairs, AB6, so sulfur hexafluoride. Okay, look how many atoms bond to central atom, 6, but central atom doesn't have any lone pairs. This is how you're going to memorize them. Okay, guys, here this is extra for you. Guys, here this is very important. Linear, except 2 atoms bond to central atom. We talked about 2 atoms bond to central atom, linear, 0 ampere. Example A, the type of molecules AB2, beryllium. This is molecule. But here, guys, all diatomic molecules like H2, N2, O2, hydrogen chloride. We know diatomic molecules, a molecule made of 2 atoms. Same or different, they are called diatomic molecules. So they are all linear. When you see a molecule made of only 2 atoms, hydrogen, this is like that, hydrogen fluoride. So you learn, this is made of a hydrogen atom, a fluorine atom, 2 atoms. So it's always linear. Okay. Trigonal planar, again, 3 atoms bond to central atom, 0 lone pairs. AB3, this is how they're shaped, guys. Here, look. In 3D. Okay, tetrahedral, and also there's bond angle in tetrahedral is 109.5 degrees. Okay, look, their shape when it's tetrahedral. Okay, example CH4, we talked about them. Trigonal bipyramidal, 5 atoms bond to central atom. Central atom doesn't have any lone pairs. Octahedral, 6 atoms bond to central atom, 0 lone pairs. AB6 like sulfur hexafluoride. Okay, and this is their shape. Band, 2 atoms bond to central atom. Look, guys, E1 or E2, 1 lone pair or 2. 1 lone pair here, 10 dichloride. Okay, we are talking about just molecules. Okay, Trigonal pyramidal. Three atoms bond to central atom. Central atom has a lone pair. Okay, here like NH3, it has a lone pair. Guys, boron, trichloride. What's the molecular geometry? How many atoms bond to central atom? First of all, we draw Lewis structure. This is like that, isn't it? Chlorine, because boron has 3 valence electrons. We talked about that it shares 3 electrons with 3 chlorines. We should not forget the lone pairs, because if we don't write lone pairs, means it's structural formula, not Lewis structure. Okay, so this shape is what? 3 atoms are bound to central atom, and means if central atom B is central atom and 3 atoms mean B3, and does it have any lone pairs? No. So AB3, we know it's what? Trigonal planar. Okay, here also we have HI. It's always is made of 2 atoms. It's the atomic molecule. It's linear. Basha. Carbon, tetrabromide. Here, how many atoms? Carbon makes how many bonds? 4 bonds. So there are 4 bromine. They bond together. It is going to be tetrahedral. CH2Cl2, guys. CH2, it might be, you must draw Lewis structure. Carbon makes 4 bonds. There are also 4 atoms. They bond. 2 of them, they're chlorine. Basha. Chlorine. And there are 2 hydrogens. 2 hydrogens. Basha. Now there are two hydrogen and 2 chlorine. They're bound to central atom. Okay, lone pairs here. Bash. Now how many atoms bond to central atom? 4. Central atom does have any lone pair? No, this is tetrahedral. Here guys, sulfur hexafluoride. Sulfur is central. Basha. If it's central, others they become B. How many B we have? 6. We have 6 fluoride. So there are how many bonds? 6 bonds. When 6 bond, it's what? Octahedral. Okay? Okay, here C must be tetrahedral. CO2, guys. CO2, you might say 2 atoms are bound to central atom. But we must know, is there carbon? It has okay, carbon makes 4 bonds. There are 2 oxygens. We learn Lewis structure. Oxygens, carbon makes 4 bonds. So there are only 2 atoms. It makes 2 bonds with each oxygens to be 8. Now carbon has how many? 8. But oxygens, it has 2 and 4, 5, 6, 7, 8. 2, 4, 5, 6, 7, 8. So CO2 is linear or bent? Linear. 2 atoms bond to central atom. Central atom doesn't have any lone pairs. We don't care about lone pairs of oxygens. Asha? Here guys, look. This example. If sulfur difluoride, this is a Lewis structure, but it's not geometrically, right? This is a Lewis structure. It's bent or linear. It looks linear, but it's not geometrically shaped. So there are 2 atoms bound to central atom. Does the central atom has lone pair? Yes, there are 2 lone pairs, so it's bent. Here, guys, how many atoms are bound to central atom? 3. Does the central atom has lone pairs? Yes, this is AB3E. So AB3E is trigonal pyramidal. Okay? That's it. This is molecular geometry, shapes of molecules. Now we're going to talk about a shape which is tetrahedral. What happens to the orbitals? In what? In in carbon atom when it makes 4 single bond. Guys, whisper theory is really useful for what? Explaining the shapes of molecules, isn't it? Was good. But if we want to know what happens to the orbitals when they make bonds, okay? So in an atom, what happens? We must know hybridization. Hybridization is very useful. So how orbitals they become rearranged when atoms they form covalent bonds, hybridization is used. What's hybridization? Hybridization is mixing orbitals of one atom, okay, and orbitals of similar energy, very close, on the same atom to produce new hybrid atomic orbitals of equal energies. Basha? Now guys, we're going to just talk about carbon. Basha? How carbon makes 4 single bonds. When carbon makes 4 single bonds, 1, 2, 3, 4, means bonds makes bond with 4 other atoms. So it's what? Not tetrahedral? Yes, example, CH4. We're going to talk about how carbon makes 4 single bond, tetrahedral shape. So, here, how does carbon form 4 single equivalent tetrahedrally arranged covalent bonds? Basha? How makes 4 single bonds? These single bonds, they're going to, the orbitals here, there must be same, because these are each single bonds, same. Basha guys, look, this is carbon's orbital before hybridization, means mixing. Guys, look, this is energy of the orbitals. 1s is the lowest, right? By the energy we learned in chapter 4. 1s is filled by 2 electrons, 2s filled by 2. Carbon 2p is filled by fills by 6, but carbon has only 6 electrons. 2 of them will be in 1s, other 2 will be in 2s, and the others will be in 2p, which are 2. Bash. Now guys, do they have equal energy to S2p? No, they don't. So in here, when 2 carbon makes 4 single bonds, the orbitals, they're going to have same energy, same shape. 2s shape is what? Is spherical, isn't it? And shapes of p, they are what? Dumbbell, right? Dumbbell shape. Their shapes are different also. So what happens? And we know ampere electrons they bond. This is 2p. It has how many electrons here? 1. But that orbital can take 1 more electrons. So when it shares, so here these electrons can be shared. It's ampere. Do you remember we talked about carbon has 4 ampere electrons? Isn't it? So how it can happen? But here in 2s, these are their carbon. First of all, we must know it has 4 valence electrons. 1, 2s, 2p, they are in the second shell. 1s is not what? Is not in the last shell. So 2s and 2p. But this is 2s. 2s is filled. These electrons can't be shared. They are paired. Paired, they can't make bonds. So what happens? Here, these electrons, first of all, when carbon is about to, when 4 hydrogens, they get closer to carbon, these electrons goes up to high energy level. So it comes here. So we're going to delete that one. Imagine. So there are how many ampere electrons now? 1, 2, 3, 4. Good, teacher. There are 4 amperes. They can be shared now with 4 hydrogens. We're talking about CH4. Okay? CH4 tetrahedral shape. We're talking about how tetrahedral shape of carbon produce. There must be 4 ampere electrons, ampere orbitals, because each orbital can get 2 electrons. If there is 1 ampere, it can take another. So when it shares with this one, when it will be shared with another orbital from another atom, so what happens? this electron, this is a row basha. So this one and this, they will be shared. This electron sometimes it comes here, right? We said this shared electrons, they are the electrons of both basha. That's why we say they must be what? They must be unpaired. Okay, good. Now we said there are 4 unpaired. This one has promoted, which is called promotion. Basha. Now there are 4 unpairs. Do they have equal energy? No. They must have equal energy. What happens? Hybridization happens. These 3 with one of the orbitals of 2s and 3 of the p, they what? They combine together. This is called hybridization. Hybrid, which mixing 2 or more orbitals of similar energy. Guys, they don't have same energy. There's energy, they're equal. They're similar. Okay? What happens? These 4, they combine together to what? To make 4 new orbitals. We call what? Hybrid orbitals. Some mixing 2 or more orbitals. Same atom. We're talking about carbon. To produce new hybrid atomic orbitals of equal energies. They must have what? Equal energies. So now they don't have, there are 4 unpairs, they get together now. When they get to combine, they make 4 new orbitals of equal energy. By energy, look, the energy is right here. They're all same. Now there are 4 ampere orbital electrons, 4 ampere orbitals, new orbitals. We call them what? Hybrid orbitals. What are hybrid orbitals? Guys, are orbitals of equal energy. Do they have equal energy? Yes. Produced by combination of 2 or more orbitals on the same atom. Okay? Leo, 1s is still there. Nothing happened to 1s because it is in inner shell. We are talking about last shell. Now, what does mean sp3? sp3 is the name of the hybrid orbitals. Name of the hybrid orbitals, or the name of the process, hybrid sp3 hybridization, we call it. So when carbon makes 4 single bonds, when carbon shares 4 ampere electrons, when makes 4 single bonds, tetrahedral shape of carbon, there are 4 single bonds. So this happens. One of the sp3 means, guys, s means one of the s. It's not one of the s has, which is 2s, orbital like s. 3 of the p, they have combined it. So we say s to power 1 means 1 of the s orbital. 3 of the p orbitals, these are p orbitals, they have what? Hybridized. They have combined. It means this. Guys, here is written. sp3 orbitals in the superscripts s on the p and 1 on the s indicates 3 p orbitals, and 1 of the s, they were included in the hybridization. Okay, in the hybridization, there are these orbitals, they have combined. sp3 means 1 of the s and 3 of the p orbitals, they have combined. sp3 means how many empty orbitals? How many ampere orbitals? 4 orbitals. Okay, 4 hybrid orbitals. Now carbon is ready to make 4 single bonds. Okay, so this is what happens, how the orbitals of atoms, they become rearranged when carbon makes 4 single bond, when makes a tetrahedral shape. Okay, so that's it. Guys, here this is just you to understand that s, it has shape. Basha, s, 2s, 1s, they have what? The shape of the electrons, electron cloud, right? Orbitals. It's s shape. When they move, they make s. They make spherical shape. Electrons in p, they have dumbbell shape. Look, we have how many p orbitals? Let me erase all. Good. No, yet. Bash. Here we have how many orbitals they combine? 1 of the s. Okay, good. One s orbital. Not mean one s like here this one. No, means one of the s orbital, which is 2s. It has spherical shape, and p shapes, each one it has a dumbbell shape. Ama orbitalica 2 3. They what? They combine. When they combine, they make four new orbitals. We call them hybrid orbitals. Amana pianonici hybrid orbital canon. So they have equal same shape. Their shape's also different. And the shape of the sp3 orbitals, they're what? There are four, four sp3 orbitals. Actually, they have same shape and equal energy. So tetrahedral geometrically will form. CH4 we said. It makes what now? It makes a tetrahedral shape. Now, this is carbon before bonding. Here, this is that, represent this one. With four oxygen, when four oxygens they make bond, they get closer, like here. When they get closer to carbon, carbon now is ready to make four bonds. So when four hydrogens they get closer, look, the shape will be like that. Hydrogens they combine with each, or look, this is one of the orbital, another sp3, another 2, okay? And hydrogens they have hydrogen whites, hydrogen's orbital that's spherical because hydrogen has only one electron, okay? That's it. This is what happens when carbon makes tetrahedral shape. So if it's become double shape, the hybridization changes. Like for example, carbon double bond with oxygen, and we have a hydrogen, we have another hydrogen. Teacher, is it same hybridization is going to be sp3? No, it's going to be sp2. But we don't learn here. What you must know only about carbon, how it makes tetrahedral shape, what happens to the orbitals. That's enough. Guys, intermolecular forces. Between molecules, we talked about their shapes. There is what? There is attraction. Here, water, guys, a glass of water, this is a molecular compound water we learned, isn't it? It's made of, maybe this water made of zillions of what? Water molecule, isn't it? Because made of molecule water. Water is a molecular compound, is a compound made of molecules. What binds the molecules of water? What? There must be a force. We call it force. It's not different than bonding. Bonding is like transferring, sharing electrons. But there is a force of attraction between positive and negative. Okay? Let's talk about it. The force of attraction between molecules are known as intermolecular forces. Between molecules, we have what? We have a force of attraction we call intermolecular force. Guys, if there is HCl, hydrogen chloride, or hydrochloric acid, HCl again, there are two molecules. Between hydrogen and fluorine, between atoms of a molecule, we have what? Look, covalent bond. But between molecules, we have intermolecular force. But intermolecular force is weaker than covalent bond. And the bond between atoms of molecules is stronger than the bond between two molecules. Okay? That's it. You must know this. An intermolecular force vary in strengths, but generally means not all the intermolecular forces their strengths are same, change with the types of molecules, but generally they're weaker than bonds that join the atoms in a molecule. What bond joins the atoms in molecule? Covalent bond. This is about this. And ions in ionic compound. One bond ionic compound. Ionic bonding is stronger than what? Intermolecular force. Or metals. Metals with metallic bonding. So we can arrange like that, guys, the order. Strengths. Metallic and ionic, they are stronger than polar and non-polar. Do you know we have two types of covalent bond? Polar electrons are unequally shared. Non-polar, they are shared but equally. So means covalent bond is between atoms of molecule. Metallic bond is between metals. Ionic is between ions. So metallic and ionic, they're stronger than covalent. And covalent bond, which is between atoms of molecule, but intermolecular force is between molecules. So covalent bond is stronger than intermolecular force. So the weakest one here is intermolecular forces. The bond, the force between molecules. And guys, for molecules, liquid molecules especially, is a good way, boiling point, to measure the what? To measure the force of attraction between particles of liquid, to know the boiling point of water, to know the strengths of intermolecular force between water molecules. Pasha, we use boiling point. Boiling point of water is 100 degrees Celsius, isn't it? It's high compared to others. But here, guys, for example, look at here. I'm a water. What about NH3 ammonia? It's negative. It's very low, its boiling point, because the bond between molecules of NH3 molecules is weak. Okay, the strength of bond. Basha? And guys, look, generally, boiling point of ionic compounds and metals are much higher than molecule substance as shown in table 7. Guys, look at here. I want to make it clear, these are molecules. They are all molecules. And polar covalent means here, for example, in NH3, the atoms, the bond between atoms is covalent. Okay, like H2O, hydrogen, and here hydrogen, isn't it? We learned that the bond between oxygen and hydrogen is covalent, but which? Polar covalent. They are unequally shared. So here between atoms of molecules, it's polar covalent, it's non-polar, and it's going to be like that. And we call non-polar covalent bonds. So here, guys, generally, non-polars, their boiling point is different. We can't make that polar molecules, their boiling point is higher than non-polar molecules. So we don't compare like that. What do we say? We say that polar and non-polar molecules or molecular compounds, their boiling point is higher than ionic and metallic substances. Molecular substance means made of molecule. Oxygen. Oxygen, we don't say is element. Yes, element. But it's made of O2 molecules. It's diatomic molecules, right? Element. We have some elements, they are molecular. Okay? What you must know, molecular substances, their boiling point, it's here written, boiling point of ionic and metals. Look, NaCl is 1413, copper 2567. Look, to become gas, they need very high temperature, their boiling point. So molecular compounds, these are molecular compounds, their boiling point is low, like water is 100, but NaCl that we use is 1400. Okay, that's it. Types of intermolecular forces. We have dipole force. Guys, there are types of intermolecular forces, and types bond between force between molecules. We have different. One of them, dipole force, is force of attraction between positive charge of one polar molecule and negative charge of another polar molecule. Okay? So it's a force between positive charge of one polar molecule, negative charge of another polar. Guys, polar molecule is a molecule that electrons, they are unevenly distributed. So the bonds, okay, generally are polar. Here, next slide here, I will talk about that molarity types, which one is polar, which one is non-polar. Polar means having dipoles. What does mean dipole, guys? HCl, do you see HCl here? Cl, it has partially negative. Hydrogen has partially positive. Why? We know bond between HCl is polar, and HCl by electron negativity difference, chlorine is 3, hydrogen is 2.1, isn't it? So chlorine, the difference is 0.9. So when it's 0.9, it's polar or non-polar? It's polar. When it's polar, the one that has high electron negativity in the molecule, we give it partially negative. Electrons are closer to it. And partially positive. I'm a molecule like a polar. This is a polar molecule. If there's another polar molecule next to it, like HCl again, hydrogen partially positive, partially negative, because it's polar. And here the attraction between positive site, and a partially positive atom, and what? And partially negative of another molecule is called dipole interaction, dipole force. I'm a dipole force. Also here, guys, there's another molecule of HCl. Again, between chlorine and hydrogen, we have another dipole force. Guys, dipole means two poles. I'm a dipolic. I'm a dipolic. So, this is a dipole, isn't it? I'm a dipolic. Also, this is a dipole. This attraction is called dipole force. Dipole means two poles. Here, partially positive, partially negative. I'm a dipolic. I'm a one. The second one, this is another one. So this is dipole interaction. Also, this is a dipole. Also, this one again. This is a dipole. So this one is also a dipole force. Okay. It doesn't mean both together is going to be dipole force. No, each one of these is dipole force. Pasha? As I said, it happens only between polar molecules, dipole force. It happens between only polars that are dipole, and the attraction between positive and negative. Polar molecules act as tiny dipoles, as I said, positive and negative because of uneven distribution of charge. When there's uneven distribution of charge, and it means electrons are not equally shared. Pasha, dipoles represent by an arrow. Guys, a dipole is represented by an arrow. Look at HCl. We didn't say chlorine is partially negative and hydrogen partially positive. Yes. So we're going to represent by an arrow. It has a head and a tail. The tail will be situated on the positive side, and the head of the arrow, guys, will be situated on the what? Negative side, partially negative of the polar. Here H2O, guys. H2O, we know it's hydrogen. These are hydrogens, and this is oxygens. We know oxygen's electron negativity is higher than hydrogen. Hydrogen partially positive, partially negative. We're going to represent by like that. And the whole, because it has lone pair, next slide I will explain. The whole molecule will be what? Will be polar. This side of the hydrogen is more positive at the bottom. Here on the top, which there's oxygen, this side will be partially negative. So the arrow will be like that, pointing towards up. Determining the polarity. How we know a molecule is polar? We know how we know a bond between two nonmetals in a molecule is polar or non-polar. What about the whole molecule? Is it polar or non-polar? The atomic molecules, HCl, H2, A molecule only made of two atoms. Okay, how we determine the polarity of the molecule, not bond where. So diatomic molecules, here it is. Polarity can be determined by only by the electronegativity difference. So it's like how we indicate the polarity of the bond. HCl example. So HCl, hydrogen is 3, as we said this 2.1. We know the bond is the difference 0.9. This bond is covalent bond and it's polar. But what about the whole molecule? Because sometimes the whole molecule, the bond is polar, but the whole molecule is non-polar. I'm going to explain. The whole molecule also is going to be polar, because for diatomic molecules, we determine the polarity by only electronegativity difference. Means if the bond is polar, the molecule is polar too. Okay? But what about polyatomic molecules, guys? Polyatomic molecules, here. Polyatomic molecules, polarity can be determined or can be affected by electronegativity difference and orientation, like shape of the molecules. Here I'm going to make it easier for you. You don't need to know the orientation or electronegativity difference, find out it. So it's the polyatomic molecules means a molecule made of more than two atoms, like H2O, NH3. Okay, so it's polar if there is lone pairs on the central atom. If there is central atom has lone pairs, like H2O, guys, H2O has how many lone pairs on the central atom? 2 lone pairs, isn't it? Oxygen, right? Oxygen, hydrogen. The bond is polar, also the molecule is polar. We're going to represent the polarity of molecules here by this sign. As the sign, the way that we represent a polar, bond polar. These bonds, they're polar. Also, the whole molecule is polar, and this side of hydrogen is partially positive. Why? Because there are lone pairs. When I give you H2O, is polar or non-polar? Draw Lewis structure. If there is lone pairs on central atom, it's lone pairs. NH3, example, another example, NH3. NH3, this is nitrogen, and there are 3 hydrogens, isn't it, Basha? We know nitrogen has a lone pair. So the bond, and here this is polar, isn't it? These are polar bonds. Hydrogen is partially positive, nitrogen has high electronegativity compared. So each bond is polar. We represent by the arrow that it has a tail. And what about the whole molecule? It has lone pairs. So it's what? Polar. Okay, Basha. Sometimes there's no lone pairs on central atom, but it's polar. When what? Atoms bond to central atom are different. When they're different, like CH3, Cl. When I draw Lewis structure, look, H, the H, but we have a Cl also. Basha, now, the atoms bond to central atom, are they same or different? Different. There are 3 hydrogens, but chlorine is different than hydrogen. So this is also going to be polar. Do you see it here? So the bonds, they're polar. Also the whole molecule is polar too. Okay? That's it. So when is going to be nonpolar? It's going to be nonpolar, a polyatomic molecule, when if the atoms bond to central atom, there must be same, and also there must be no lone pairs on central atom. Example, CH4, CO2. This is CH4. This is carbon. This is hydrogen. Hydrogen, hydrogen, hydrogen. Another hydrogen here. So how many atoms are bonded to a central atom? 4. Okay. Are they same? Yes, same. They are tetrahedral. and there's no lone pairs, so it's going to be non-polar. Guys, bonds are they what? Okay, and here this is going to like repel each other. Okay, the whole why it happens because the all sides they are symmetrical. Here this occurs because individual atoms they are symmetrical, means each side each bond is equal to other bond. The polar distribution of electrons around the central atom are same, they cancel out each other, the bonds. Okay, okay, here this is we have carbon and oxygen, CO2. How many atoms are bound to central atom? Two. Is there any lone pairs on central atom? No. So this is polar. Okay, that's it. Carbon, no molecular dipole. No molecular dipole. Okay, that's it. A polar molecule can produce a dipole in a nonpolar molecule by temporarily attracting its electrons. Guys, polar, we have dipole force. What about between a polar and a nonpolar? There is a force of attraction. How it happens? This is water, which is polar. Oxygen is the atomic molecules of same type atom. It's nonpolar. There's no poles, right? But the polar molecules can produce a dipole in a nonpolar. By what? Attracting its electrons. Guys, these are oxygens, isn't it? They have valence electrons. So they have like 2 lone pairs, and there are how many? There are 4 electrons, they're shared, isn't it? So these partially positives of oxygen here attracts these, okay? Attracts what? These electrons. To which side? To this side. So more electrons going to come, look here. The positive pole of water, which what? Positive. Hydrogen is partially positive. Attracts the outer electrons of adjacent oxygen molecule. The oxygen molecule then has induced a negative pole. This side, look what happens. Next step. Because electrons, they come to this side, they are going to be pulled by hydrogens. So now this side will be, it makes a dipole, makes 2 poles, partially negative, because more electrons they have from this side, the shared electrons. But this side is going to be partially positive. And this attraction between partially negatives and partially positive, there's what? There's a weak attraction. But this, it makes a short range intermolecular force, but weaker than the dipole force, the weaker than the between polar molecules. Okay, that's why a polar makes a non-polar and makes a dipole in a non-polar. So then an attraction happens. That's why in water we have oxygen, dissolved oxygen. Why it happens? Because of this attraction. That water attracts the electrons of another oxygen, and oxygen is going to be a dipole, like partially negative, partially positive, and partially negative with hydrogens which are partially positive. There will be a weak attraction between them. Okay, hydrogen bonding is a dipole force. Teacher means it's between 2 polars. Yes, it's between 2 polars. But guys, what's the difference? Those compounds, they contain hydrogen fluorine. يعني unbonded habit لهر molecule hydrogen habit that has bonded with a fluorine, with oxygen, with nitrogens. P-aniline, we call them highly polar. Basha, we call them highly polar. Basha, when they are highly polar, when these bonds in a molecule is highly polar, the molecule is polar. If there is another molecules, the hydrogen with another lone pairs of these of fluorine, oxygen, nitrogen, and another molecule is called hydrogen bonding. It's going to be very strong. So it's going to be between hydrogen and nitrogen. Hydrogen is it has very low electronegativity. Nitrogens that they have lone pairs also. So in the bond is going to be highly electronegative, and hydrogen less electronegative. So it's going to be a strong intermolecular force happens. So compounds they contain these types of bonding is going to be highly polar, like HF here, unbonded is high. This molecule also is highly polar, these bonds, okay, and the molecules also. So hydrogen and fluorine is highly polar. The attraction between guys, hydrogens of hydrogen atom and lone pairs hydrogen atoms are in what? In a molecule. There must be here written in a molecule, we can say. Lone pairs of highly electronegative atoms. And in lone pair یعنی چی؟ Oxygen, nitrogen and fluorine in another molecules. Nearby molecules known as hydrogen bonding. Here guys, this is H2O. Basha is a polar. There is hydrogen, oxygen, oxygen, hydrogen. This is a what? Highly polar bonds. So we can say between hydrogen in a molecule and lone pairs or oxygens in another molecule is called hydrogen bonding. Okay? Hydrogen bonding. It doesn't happen only between hydrogen, fluorine, oxygen. It happens between hydrogen in a molecule, for example water, with nitrogen with another molecules. It's also hydrogen bonding. Here between hydrogen and fluorine, guys, there must be hydrogen here also. There must be fluorine. We represent by dots mostly, okay? So the attraction between fluorine and hydrogen in another polar, highly polar molecules is going to be what? Is going to be and it happens between two polar molecules, and the polar molecule must contain hydrogen and fluorine, or oxygen, hydrogen, nitrogen, hydrogen, nitrogen bonding. Here it contains this molecule. So the attraction between hydrogen and fluorines in two different molecules is what? Hydrogen bonding. Okay, and hydrogen bonding is the strongest. Hydrogen bond is the strongest intermolecular force. Okay, you must know it's very, very strong, and but it's still intermolecular force is still weak compared to ionic and metallic bonding. So hydrogen bonding also, it's what? It's dipole force, but not all the dipole forces is hydrogen bonding, like hydrogen chloride. Basha, hydrogen chloride, is there a hydrogen oxygen, hydrogen nitrogen, hydrogen fluoride bond? No. So if there is another hydrogen chloride, so this bond is going to be, this is what? Partially positive, partially negative. But this is not hydrogen bond, it's only dipole force. Okay, because it happens between hydrogen in a molecule and fluorine, oxygen, nitrogen is another molecules. Okay, guys, even noble gas atoms, molecules that are not polar, they experience a weak intermolecular attraction force. You might say noble gases, they don't make any attraction, they don't bond. Okay, is there any attraction between them? Yes, we call London dispersion forces. How that happens, guys? In any atom or molecule, polar and non-polar, electrons are in continuous motion, and they move very quickly around the nucleus. As a result, at any instant, at any moment, the electron distribution may be slightly uneven. Look at here, which is helium. We're talking about two heliums, how they what? They make a force of attraction between each other. This is for a moment it might be slightly uneven electrons. I mean, normally it's like that, two electrons, but for a moment it might be uneven distribution of electrons, like this momentary uneven charge creates a positive pole in one side and another in negative pole in another part. So look guys, this side for a moment maybe two electrons of helium becoming the same side because of this motion of electrons. So this side of the atom of helium atom we're going to talk about is going to be more negative, isn't it? This side is going to be more positive, so we give it this side partially positive. This is partially negative, isn't it? Then this temporary dipole can induce a dipole in neighboring atom or molecules like helium. This is also helium atom. We're talking about two helium atom. Okay? It says I'm partially positive, attracts the electrons in another helium atom which is next to it. So when it attracts, what happens next? The electrons, and this is that one, partially this is negative, this is positive, partially positive this side, the tail. So this electrons, they come to this side, okay, because they will be attracted by the partially positives here, okay. Now the electrons, they come to this side will be negative, this side will be positive. So partially is partially negative, this side is partially positive, because this side of the atom is more positive. So there will be a weak attraction force between them. Okay? So this attraction is called London dispersion forces. It happens between noble gases and also between like two non-polars. Guys, is there any attraction between non-polars? Non-polars, there is no poles. But by the even distribution of electrons, because electrons, they are in continuous motion, they move for a moment, maybe electrons, uneven distribution of charge happens, electrons become one side, this side will be negative, makes partially negative, other side partially positive, other atoms, molecules too. So and London dispersion force, it happens. But guys, this London dispersion forces happens not only between noble gases and non-polars, because it happens also between all atoms and molecules. Any atom in nature, any molecule in nature, polar, non-polar, metal, non-metal, there's that attraction. It's very weak. But the only attraction between only intermolecular force among noble gases, atoms, and non-polar molecules is London dispersion force. But in polars, for example, between metal atoms, we have metallic bonding. We have also a London dispersion force, but it's very weak, and like we ignore it. Okay, but the only force for non-polars and noble gases is important because there is not any other force of attraction. So is the weakest intermolecular force, guys. Strength of intermolecular for hydrogen bonding stronger than dipole, and London dispersion is the weakest intermolecular force. Basha? London dispersion force depend on motion of electrons, because this motion of electrons causes that uneven distribution of charge happens, that more electrons become the same side, partially negative, partially positive happens, and attracts the electron of another atoms, so makes two poles and a weak attraction force happens. But when there are more electrons, with the strength increases, is going to be stronger if the number of electrons in the attracting electrons molecules increases. Okay, if this increases, for example, between helium, it's a helium and helium, so it has two valence electrons, and we have argon. Okay, argon, it has how many valence electrons? 8. When number of valence electrons increases, what happens? this force of attraction, London dispersion force, is going to be stronger. So which one, the bond between argon is it stronger than the bond between hydrogen helium Marsha? Helium, it has 2 valence electrons, but argon has 8. So the force of attraction between argon is stronger than the force of attraction between helium, because number of valence electrons argon is more than. So it's going to be more negative, more partially positive. Okay? This is the section review and answers. You can check it. Thank you very much. Inshallah, next video we will talk about chapter 7. Okay? Naming of compounds. Okay? See you next time. Bye.